Hi, my name is Vic, and today we're going to learn how to build a neural network from scratch in Python. We'll start out by covering the theory of neural networks and how they work internally, specifically how we use them to make predictions, and then how we correct the parameters of a neural network to make better predictions. Then we'll use what we learned to fully implement the forward and backward passes of a neural network in Python, and then we'll train the parameters using gradient descent. And by the end, you'll have a full neural network that you can use to predict tomorrow's weather. All right, let's get started.
In the last lesson, we learned how to use gradient descent to train a linear regression algorithm. In this lesson, we're going to extend what we did last time and build a multi-layer neural network. To start with, let's talk about why we need neural networks to extend linear regression in the first place. So in the last lesson, we used a dataset on weather. And what we were trying to do is predict tomorrow's temperature using today's temperature. So let's go ahead and read in that data set again. So if you're following along, your path may be a little bit different from this, but just make sure you load in the data at the right path. This command is just filling in any missing values in the data. And then I'll make a little scatter plot of Tmax and Tmax tomorrow. All right. So when we use linear regression to predict one variable from another, we want there to be a linear relationship between those two variables. And as you can see, it looks like there is a linear relationship between today's temperature, Tmax, and tomorrow's temperature, Tmax tomorrow. But it's not a perfect linear relationship. And we can use the .corr method on a data frame to see what the correlation coefficient is. And it's 0.81. Basically, the closer the correlation coefficient is to 1 or -1, the stronger the linear relationship. Now, if there was a perfect linear relationship between Tmax tomorrow and Tmax, we would see a correlation coefficient of 1. So whenever Tmax increases, Tmax tomorrow will also increase and vice versa. But that's not quite the case. There's a very, very strong linear relationship, but it's not a perfect linear relationship. So let's take a look at what it would look like if there was a perfect linear relationship. So we'll go ahead and import matplotlib.pyplot as PLT. And then we'll again draw our scatter plot from last time. But on top of this scatter plot, we're going to draw a prediction line, a linear regression line, using the coefficients that we calculated last time. So let's write a little function called prediction. It's going to be a lambda function. The nice thing about lambda functions is you don't need to write as much code to define them. And W1 is our weight on our input variable, which is Tmax. That's our X value. And B is the bias. So we multiply our input number by the weight and we add in the bias to get our prediction with linear regression. And what we'll do is we'll go ahead and plot that line. So we'll set one X point at the bottom left of the graph, one X point at the top right, and then we'll make predictions for both of those points. So this is my prediction for 30 and my prediction for 120. And this will go ahead and draw a line for us over our plot. So we can see we have our plot with all of the different points for Tmax and Tmax tomorrow, our scatter plot. And on top of the scatter plot, we have a line. So this line is the best linear regression can do to try to predict Tmax tomorrow. So if we change our weight at all or our bias at all, the error will actually increase. So let's actually take a look at that. So let's import NumPy as NP. And let's define a function called MSE, mean squared error, the same function from last time. And all this will do is return the error. So it's just the actual minus the predicted squared. So that's mean squared error. And we'll just print out the mean squared error between tomorrow's temperature, Tmax tomorrow, and our prediction for Tmax tomorrow, given this function. So let's print that out. And we can see our mean squared error is 22.89. So we can print this out also with slightly different weights and biases by passing the new weights and biases into our function. So let's try this with a weight of 0.83 instead of 0.82. And we can see our error actually goes up. We can also try it with a bias of 13, and we can see our error goes up in that case too. So basically 0.82 and 11.99 are the best fit parameters for linear regression, but they still don't fit the data perfectly. And the reason for that is there is a non-linear component to the relationship between Tmax and Tmax tomorrow. So sometimes when Tmax goes up, Tmax tomorrow also goes up, but sometimes Tmax tomorrow goes down. And our linear regression algorithm doesn't have enough capacity to represent that relationship. So you can think of capacity as the capability of the network to represent a complex relationship. And basically, the more parameters a neural network has or a machine learning algorithm has, the greater its capacity generally, which means the more complex input data it can represent. So in this case, our linear regression only has two numbers, right? And with those two numbers, it can't represent all of the complexity in the interaction between Tmax and Tmax tomorrow. All right. So there are a few things we're going to do to solve this and to really model the non-linear component of the relationship between Tmax tomorrow and Tmax. So first, let's take a look at what this non-linear component looks like. All right, so what we're going to do is we're going to cut our Tmax up into bins. So what pandas.cut does is it makes equal width bins out of our temperature range. So let's look at these bins. So we can see that these bins are basically categories. So we're categorizing each temperature in terms of what part of the temperature range it falls into. And at the bottom here, you can see the valid ranges. So if a temperature is between 37 and 41, we put it into the first bin, 41 to 44 is the second bin, etc. Then what we'll do is we'll calculate the ratios between data Tmax tomorrow minus the bias, which is 11.99 that we calculated, divided by data Tmax, to see how the ratio between Tmax tomorrow and Tmax changes with the value of Tmax. And then we will create a binned ratio, ratios.groupBy Tmax_bins.mean. All right, so let's take a quick look at binned ratio. All right, so what this is doing is it's showing us how the relationship between Tmax and Tmax tomorrow changes as Tmax changes. And we can actually plot this out so you can get a easier look at it. It's not easy to look at a table of values. So plot bin Tmax versus our binned ratio. Calculate bin Tmax. Data Tmax.groupBy Tmax_bins.mean. So we're just finding essentially the center point of each bin, and then we're plotting them. All right, so we can see that it's not a constant ratio, right? It's not like, hey, we always take Tmax and multiply it by some number to get Tmax tomorrow. Instead, the number you have to multiply Tmax with changes as Tmax changes. And intuitively, this makes sense, right? If today is really, really hot, a record high, 120, it's probably going to be colder tomorrow, a lot colder tomorrow, than if today is just an average temperature, right? If today, let's say it's usually 50 where you live, Fahrenheit, not Celsius, and today is 50. So odds are it may actually just be 50 tomorrow. But if today is 130, a record high, odds are very, very high that it's going to be a lot colder tomorrow. So that's an example of a non-linear relationship and something linear regression cannot model. All right. So there are a few things that neural networks do to actually fix this issue and to make linear regression essentially more robust, because neural networks really are built on top of linear regression. But neural networks do three key things. They add in a non-linear transformation on top of the linear transformation. They have multiple layers which capture interactions between features, and they have multiple hidden units per layer. each of which have slightly different linear and nonlinear transformations. So I'm going to talk through this and show you how this actually works. All right, the first thing we'll talk about is the nonlinear transformation on top of the linear transformation. So the most common nonlinear transformation used in neural networks is called ReLU, and the idea is that any value below 0 is set to 0. So you recall the linear regression equation, which just says y equals wx plus b. So our prediction equals the weight times the x value plus b. When we add a nonlinearity, we basically say y equals ReLU wx plus b. A little bit more complex than this because we don't do ReLU on our output layer, but you can essentially think of us applying the nonlinearity over the top of the linearity. All right, so let me actually show you what a nonlinearity looks like. So let's say we have a range of temperatures, and I'll use the NumPy arange function to actually create this. So this is going to be from -50 to 50, and we'll have a space of 1 between each number in our range. And then we'll go ahead and plot these. So we'll plot temperatures, and then numpy.maximum 0 prediction temps. So basically what this is implementing is this equation right here. We're taking our prediction from earlier, our prediction function. We're predicting what tomorrow's temperature should be, and then we're applying the nonlinearity on top of it. All right, so it ends up looking like this. So any value below 0 is essentially truncated, moved back up to 0. And this makes the relationship between the input and the output non-linear, right? It may look really simple, but this nonlinearity is really the key to neural networks and their power. So this looks really simple, but is actually really, really powerful. Now, of course, if all we did was add a nonlinearity, we'd actually get terrible predictions. Because right now, if our temperature for today is -40, we're always going to predict that tomorrow's temperature is 0, which is usually going to be very, very wrong. So what neural networks do to account for this is they have multiple layers. And they usually do not use ReLU at the output layer. So what this looks like is this. So we'll have W1, B1, and then we'll have W2 and B2. So this is an example of 2 layers in a neural network. The first layer is the ReLU and the linear regression part, W1 times X plus B. And then the second layer multiplies the output by another weight and then adds another bias. So this is an example of a 2-layer neural network. I actually should be doing Y here. Y hat is the predicted Y value, just to differentiate it from the actual Y value. So again, let me just plot out what these 2 layers would look like. So we'll generate our range of temperatures, and we'll say layer 1 equals numpy.maximum 0 prediction temps. So this is the exact same thing we saw in the last graph. And then we'll go ahead and apply layer 2, which on top of that is going to apply another prediction. Now, layer 2 will have different weights and biases from layer 1. So I'm just going to set it to have a weight of 0.5 and a bias of 10. But really, the neural network will automatically learn the weights and biases, which I'll show you later on. Okay, so that's layer 1 and layer 2. And then we can do plt.plot temps layer 2. So we'll be able to see what it looks like at this point. And I'm just going to set the limits of the plot properly so you can see the entire plot. Okay, so slight improvement, right? Instead of predicting 0 every time, we're now predicting 10. And the network would be able to learn the correct bias. So it would be able to learn the correct bias to reduce error. So this bias might end up being some number other than 10. But we're still predicting a constant value for any number that output a 0 in layer 1, right? Which isn't going to give us a ton of accuracy. because obviously anytime we make a prediction and our input temperature is below 0, we're not always going to end up with the same temperature tomorrow, right? It's going to result in very, very high error. So the nonlinearity hasn't quite solved our problem yet. And to fully solve our problem, we actually have to do one more thing, which is adding multiple hidden units per layer. All right, so let's see what this looks like. So let's go back to layer 1. So let's say we have layer 1 unit 1, which I'll call layer 1 underscore 1. And let's say that's just from earlier what we used to predict layer 1. And let's say we also have layer 1 unit 2. And for that, what we can do is, again, numpy.maximum 0 prediction, but we'll have a slightly different set of weights and biases this time. So let's use 0.1 as our weight and 10 as our bias. Again, the network will calculate the weight and bias automatically, but I just want to show you an example. So let's just go ahead and plot our temps with layer 1 unit 1. And we'll, on top of that, plot our temps with layer 1, unit 2. All right, so we can see two lines here. With one line, we've truncated all of the outputs below a certain value to 0. With the other line, we haven't. And the reason for that is we multiplied by a very, very small number, right? So we can take a look at our layer 2 numbers. Layer 1, 2 is what I should be looking at. Our ReLU function was never activated here. Because, for example, let's say you have a very, very small number, like negative 50, and then you multiply it by 0.1, and then you add 10. It's going to be a positive number, right? And all the way up to negative 100, which I hope none of you live in a place that gets to negative 100. That would not be optimal. So really, this weight and this bias ensure that the ReLU function is never activated, right? Which means that we're passing through all of the information about the input temperature, but in one of the units. The other unit is actually activating ReLU and has a bunch of 0 values. Now, the real power comes when we actually add these two together. So let's add these two together. And now we can see we have a non-linear relationship, right, between our input and our output, but we haven't completely lost the input signal. Right? If we input negative 40, we're going to get a different result than if we input negative 20. But the network has still found a way to make this relationship nonlinear. And if we add a lot more units, we can add more and more complex nonlinear relationships. So, for example, let's say we want to do layer 1, unit 3. And we're going to do ReLU again, but this time we'll pass in a slightly different set of weights. Let's say I'm going to set my bias to 30, and we will add in layer 1, 3. Prediction. All right, so you can see we have this non-linear relationship here. Let me actually up this to 0.4. 6. So you can see how this nonlinear relationship starts to change as you add in more units and as you modify the weights on the units. I was trying to find the right parameters to show you a more complex line here. But yeah, you can see with 3 layers and the correct weights, the network can learn a much more complicated relationship. Okay, so let me show you a quick diagram that indicates what this looks like. So this is an example of a 2-layer neural network. So we take our Tmax value, we input it. In unit 1, we multiply by weight 1 and we add bias 1. Then in unit 2, we multiply the input by weight 2 and add bias 2. Then in the output layer, we essentially take each of the values from layer 1, from each unit, and then we multiply by different weights and add in a bias. So let me actually show you what layer 2 would look like here. So layer 2 would equal layer 1, 1 times, let's say the weight between layer 2 and unit 1 in layer 1 is 0.1. Then we take layer 1, 2 times 0.3 plus layer 1, 3 times 0.4. In reality, the network would be learning these values. I'm just making values up just for illustrative purposes. And then we would add in another bias. So output layer 2 here. And we can see it can learn an even more complex function here. All right, so this is a basic diagram of a neural network, and hopefully that helps you build the right intuition for how neural networks work and the three key principles. Nonlinearity, so in this specific case, we use the ReLU nonlinearity, which sets any value below 0 to 0, multiple layers, and multiple units. And some neural networks can have thousands of units in each layer and can have dozens of layers. So it can get really complicated, more complex than we can actually visualize properly. But these basics apply in any neural network. All right. So let's talk a little bit about how we can calculate layer outputs more efficiently. It's going to get annoying to do this, to write out W1, W2, W3. So how we actually do this is we put all of our weights and biases into matrices. So for example, in this case, we have two input temperatures, 80 and 90. And this would be a 2 by 1 matrix, 2 rows and 1 column. Then we would multiply it by a 1 by 2 matrix. These are our layer 1 weights. So it would be 1 row and 2 columns, and add in our layer 1 biases. So let's see what that looks like. So when we're multiplying matrices, we take the first row, we multiply by the first column. Then we take the first row, multiply by the second column. Then we take the second row and multiply by the first column, then the second column. So matrix multiplication is essentially a really efficient way to take inputs and multiply them by multiple numbers, just like we did here, right? Where we in layer 1 we took our input and we multiplied it by different numbers. We took our input temperatures, multiplied them by 0.1, by 2, and here 0.82. So this is a way to essentially do all of that at once. And once we do matrix multiplication on this particular set of data, here's what we get. So we take 80 and 90, we multiply by our weights, we end up with this 2 by 2 matrix. So when you multiply matrices, you end up with the same number of rows as the first matrix and the same number of columns as the second matrix. So what we're doing here is we're taking 80 and multiplying it by 0.8. So that's what you see over here. Then we're taking 80, multiplying it by 0.1. That's what you see in the top right. Then we take 90, multiply by 0.82. That's what you see in the bottom left. And then take 90, multiply by 0.1. That's what you see in the bottom right. And then we add in our biases. So our biases are a 1 by 2 matrix, and we essentially add our biases into each row. And after this happens, we've calculated basically 2 units in our next layer. So this would be equivalent to calculating layer 1.1 and layer 1.2 for each of our inputs. And we can increase our number of inputs. This is only 2. We have a lot more temperatures than that. And as we increase our inputs, we'll add more rows to our output. Because remember, our output has the same number of rows as our first matrix that we multiply. Okay, now this may not be super clear, but let's actually code it, and it's going to get a lot more clear, I promise you. I'm going to use a package called tsensor, which just makes it easy to visualize what matrix multiplication is doing. So we're going to create an array called input. If you know Python, you're probably yelling at me right now because I'm overwriting a default keyword, but don't worry about that. It's all a demo. Don't try this at home though. All right, so input is going to equal an array, and each of these is going to be a different row. So 80, 90, 100, 120. And let me actually just display input so you can see what it looks like. tsensor. All right, so we can see our input, and if you want to just check out the number of rows and columns, you can use the handy shape property in NumPy, which shows us this is a 5x1 matrix. All right, then we can create our layer 1 weights. So this will be another NumPy array. It's going to be 0.82 by 0.1. All right, so this is going to be a matrix with 1 row and 2 columns. Then we're going to create our L1 bias, which is going to be another array, 11.99 and 10. So this will be another 1x2 matrix. So you don't need this with tsensor.explain part. I'm just using this to generate a diagram of the multiplication. But the matrix multiplication part is down here. So we're going to say input at is the matrix multiplication symbol in Python. Okay, so we're taking our input, we're multiplying it by the weights, and we're adding the bias. Exact same thing we did before. And here, tensor sensor actually outputs this cool little diagram so you can see what happened. So our output has 5 rows and 2 columns. Our input had 5 rows and 1 column. We multiplied it by a 1x2 matrix and then added in a 1x2 matrix, and we ended up with 5x2. And we can take a look at L1 output as well. And we'll see what we ended up with here. All right. It's bothering me that the numbers aren't exactly the same. It's because I made a little typo in the weight. All right, so this is the exact same thing that we did in the diagram, just in code. And hopefully, since you've seen it a couple of different ways, it's easier to understand what's happening now. If you're still not getting matrix multiplication, I really urge you to just do a quick refresh on it. It's a really critical part of training neural networks. All day is just understanding shapes of matrices that you multiplied. Okay, now on top of this, we can apply our activation function, which is just reloop. So it's np.maximum L1 output, comma 0. So this is doing exactly what we did before. And then we'll take a look at L1 activated. So we can see we set one number to 0 because it was below 0 before. All right. So what we're doing here is we're using matrices instead of individual numbers as part of our multiplication. So we can rewrite our equation to look like this. So our layer 1 output equals capital X, capital W underscore 1 plus capital B underscore 1. So this just means take our matrix of X inputs, multiply by our matrix of weights for layer 1, and add in our matrix of biases for layer 1. All right, now we can go ahead and apply layer 2 in a similar way. So this is the equation for the full neural network, including layer 2. And here's a little diagram also. So we take our layer 1 output, we multiply by our layer 2 weights, and add in our bias. So layer 1 is a 2x2 matrix. We're multiplying by a 2x1 matrix. So we end up with 2x1. So a handy way to think about this is your weights. The first number, the number of rows in your weights, is the same number of columns in your input. And the number of columns in your weights is the number of features you want to output. So in this case, we want to actually output a prediction, just a single number. Okay, so let's take a look at this. So we can initialize our layer 2 weights. So this is just the same thing as here. It is a 2x1 matrix. We're going to initialize our L2 bias. It's just one number. And then we're again going to use tsensor.explain. We're going to say our output equals L1 activated times our L2 weights plus our L2 bias. And we'll take a look at our output. All right, so we get our handy little map of how we did our matrix multiplication and addition, and we get our outputs. All right, so this is basically how we make predictions in a neural network. We take our weight matrix for each layer, we take our bias matrix and we just do repeated multiplication by the weight, add in the bias, apply a nonlinearity, do it again for each layer. And basically, if you want more units in your layer, you just add more columns to your weights, right? Because remember, we had 2 units in layer 1, which corresponded to 2 columns in our weights. And in our layer 2, we only had 1 unit, which corresponded to 1 column. It's all matrices. All right, so this is what's called the forward pass of a neural network. When we know our weights and biases, we pass our input through the forward pass to get our prediction. And this output here is our prediction. Now, obviously, if we don't have a way to calculate our weights and biases automatically, that's not very useful. Luckily, the technique we learned last time, gradient descent, is exactly how we can calculate our weights and biases. All right, so the way we do it is we have our output. Now we can use mean squared error to find the error between our output and the actual values. Okay, so let's say these are some Tmax and Tmax tomorrow values. So this is essentially a lot of rows and 1 column is the way to think about it. It's a little bit hard to define this in NumPy. So there you go. That's Tmax and Tmax tomorrow. So our Tmax tomorrow values. So we can define our MSE function again. So I did this. I'm just going to show you what it looks like again. It's just the actual value minus the predicted value squared. And if we wanted to calculate our MSE, we could pass in our Tmax tomorrow, and we could pass in our output. And this basically gives us our mean squared error for each of our input temperatures. Now, remember, with gradient descent, we need to actually find the gradient of our loss function, right? The rate of change. So as I change the input to the loss function, how does the loss function actually change? So luckily, the gradient of mean squared error, as we saw last time, is not very complicated. We just pull this power of 2 down. And I'm going to leave the first term out just to make things simpler. And it'll just be predicted minus actual is our gradient. And this basically tells us how much we need to adjust our prediction to reduce our error. Forgot my return statement here. All right. Okay, so we now have the gradient of our loss with respect to the output of the network. So the next thing we need to do is something called backpropagation, which will enable us to pull the gradients through the network and use it to update the weights and biases in the network. So let's first visualize how our forward pass looks. So this is the forward pass of our network. We start at the input layer where we pass in our Tmax values. We multiply our values by the W1 matrix in layer 1, the first set of weights, and then we add in the first bias to get the output of layer 1, which we then pass through the ReLU function and pass into layer 2. And in layer 2, we multiply the output of layer 1 by W2, which is the second matrix of weights, the weights for layer 2, and then we add in another bias. And this gives us our output, which we then use to calculate the loss. All right, so to do a backward pass, as you may have guessed, we basically reverse these operations through the network. So let's visualize what the backward pass looks like. Let's visualize this. So the goal of the backward pass is to essentially calculate the partial derivative of loss with respect to each parameter in the network. So we start out with our loss with respect to the output, which was the output of our MSE grad function just now. And this is what we're going to call our layer 2 output gradient. Then we're going to use that to update the layer 2 weights. So we're going to multiply the input to layer 2, the layer 1 output in the forward pass, by the L2 output gradient to get how much we need to update the weights by. We're going to update the bias by the average of the output gradient. Then we're going to pass the gradient through to layer 1, We're going to multiply the output gradient by the layer 2 weights to get the layer 1 output gradient. We're going to pull the gradient across the ReLU function, and then we are going to use that to update the weights in layer 1 and the bias in layer 1. All right, if you don't know how these operations are going to work yet, don't worry about it. I'm going to show you how each of these operations work and why they work. So the first operation we're going to do is pulling the output to calculate the weight gradient for layer 2. So this piece right here. So let's go ahead and calculate this. So first we will assign a variable called output gradient, which is going to be the MSE grad, just Tmax tomorrow and output. So this is just our gradient that we're calculating with the MSE grad function. And then I'm going to, so I don't have to keep typing out tsensor, I'm just going to have a little shortcut for it. And I'll say with exp, define our layer 2 weight gradient as the output of layer 1 after the nonlinearity, after ReLU is applied, multiplied by the output gradient. And then we can take a look at our layer 2 weight gradient, see what it looks like. All right, so you can see here we took a 2x5 matrix, that was the output of layer 1 in the forward pass, and we multiplied it by our 5x1 output gradient, which gave us two numbers, 2x1 matrix, which tells us the gradient with respect to each of the values in our W2 matrix, our weights for layer 2. So why does this operation make sense? So to understand why this makes sense and why this gives us the partial derivative of the loss with respect to the W2 values, let's take a look at this operation in more detail. All right, so this is the forward pass of the network. So this is when we take the output of layer 1 and we multiply it by the layer 2 weights to get the output. And I haven't used numbers in this diagram. I've instead just represented each value by a different identifier. So I11 is the first row, first column of our outputs of layer 1. I12 is first row, second column, and so on. And then in the output, we get two output values, so essentially one prediction for each row of input data. And we can see what makes up each of these outputs. So each output is the first column value in layer 1 times the first weight plus the second column value times the second weight. So you can see how that looks. So another way to think about this is we're actually connecting each output of layer 1 to the output of layer 2 through the weights. So this is how that looks. So you take each of the first values in the first column of the layer 1 output, and through weight 1, they're connected to each of the outputs, right? We take I1_1, we multiply it by weight 1, and that makes up part of our first output value. Same thing with I21, we multiply it by weight 1, and that makes up part of our second output value. So the weight is really connecting certain outputs of layer 1 to certain outputs in layer 2. So that's one way you can think about the weight. And by connecting, I just mean the weight is multiplied by the layer 1 outputs to get the layer 2 outputs. And I'm leaving the bias out here. It's not really necessary for this, and it simplifies things if we leave it out. So sorry, bias. Okay, now what we can take a look at is how the gradient flows. So this is the output of layer 1, but transposed. So this time we take I11, we basically take I12 and I21 and swap them. So the rows turn into the columns and vice versa. And then we can multiply this by the output gradient to get the weight gradient. So this is the operation we did in the code here. We took the output of layer 1, we transposed it, and then we matrix multiplied it by the output gradient. So that's the same thing that's being shown in this diagram. So what we want to figure out is how much do I need to adjust W1 and W2 to lower error? And both W1 and W2 are used in all of the output parameters. So it's not exactly straightforward to figure it out, right? If we raise W1, that might end up improving our our prediction in one of the outputs and making the other prediction worse, for example, right? Depending on how the exact values look. So the way we figure out how much to adjust each of the weights is we figure out what the weights are scaling, what inputs the weights are connected to, right? So in this case, weight 1 is multiplied by both I11 and I21. So how much we want to adjust the weight depends on the values of I11 and I21. Because if we say add 1 to weight 1, we increase the first output by the value of I11, right? If W1 equals W1 plus 1, we're multiplying W1 plus 1 times I11. And it increases the second output by I21. So I'll show you how this looks again in just a little connection diagram with some arrows. So we can see how each output of layer 1 connects to one of these outputs, and through that output connects to a weight. And this is a similar diagram to what we looked at before, where in the forward pass, each output of layer 1 is connected to a weight, and through that weight connected to an output. But this is the backward pass, and we're essentially reversing that operation. We're saying, okay, which input from layer 1 made up which output, made up part of which output, and which weight was it connected to? So we're reversing that operation to figure out how much we need to adjust each of the weights. So this is what we end up with when we calculate it out. If we plug in the numbers from the first 2 rows in our layer 1 output and our first 2 rows in our output gradient, this is how that multiplication looks. All right, this is probably the most complicated part of training neural networks, backpropagation. So if you're not quite getting it, don't worry about it. I've linked to a document in the description where you can actually read through this description again at your own pace and figure it out. I would also recommend playing around with this matrix multiplication here and actually look at the values and see how the values change. So you can look at the L1 activated and output gradient and just see how the values change as you multiply them. Because really, these connection diagrams show you what's happening. We figure out every value in the layer 1 output from the forward pass that was multiplied by a weight, and then we figure out which output it's part of, and then we reverse that operation by multiplying the layer 1 outputs by the output gradient. And this tells us how much we need to adjust each of our weights. It's equivalent to taking the partial derivative of loss with respect to the layer 2 weights. So I'll write out the math for you, just in case you don't trust me. So here's what we're doing. We're taking the partial derivative of the loss with respect to the second weight matrix. And due to the chain rule of partial derivatives, how we can do that is by doing this. If we want to take the partial derivative of loss with respect to weight 2, we multiply the partial derivative of loss by the partial derivative of x times W2 with respect to W2. All right, so this partial derivative of loss here is actually equal to this. Just for simplicity's sake, I left off the denominator just to make it a little bit simpler. All right, so this is the equation we need to solve. So the partial derivative of loss with respect to the model output is the first piece that we need. That's called the output gradient. And that's the output of our MSE grad function. So this is the partial derivative of loss with respect to the output of layer 2. Then what we do is we multiply that by the partial derivative of the output of layer 2 with respect to the weights. And that is just x. That's the input to layer 2, or the output of layer 1, which is what we did here. We took the output of layer 1 and we multiplied it by the gradient to get the weight gradient. All right. And one way to verify partial derivatives, if you want to really get under the hood, is a Python library called NumPy. It can't really differentiate everything perfectly, but it's free and it does a pretty good job. So what we can do is define 2 symbols in NumPy. So these are basically the same symbols you see here, the building blocks of math equations. Then we can define our equation, which is just x times w. So this is the output in the forward pass, not including the bias, which we just omitted for simplicity, but it's the output of layer 1 times the layer 2 weights. And then we can use the diff function to actually differentiate this and get the derivative with respect to W. And as it turns out, it is X. So essentially what we're going to do is multiply this out. So we can say that the partial derivative of our loss with respect to W2 just equals the partial derivative of loss times X. So that's what we end up with. And basically, we're applying this chain rule to find the updates for every parameter. Don't worry, I'm not going to show you the equation for every single parameter update, but as we update the bias for layer 2 and the weights and bias for layer 1, this is basically what we're doing. We're just applying the chain rule, which says take the partial derivative of one thing times another thing to calculate the larger partial derivative. So it's basically breaking the partial derivative into pieces. All right, so the next thing we can do is calculate the derivative with respect to the bias. So we'll find our L2 bias gradient, and that's just going to be the mean of our output gradient. And the reason for that is the layer 2 bias is directly added to the output. So when we go back and look at our forward pass diagram, we can see that B, which is our layer 2 bias, is added in to get our layer 2 output. So any change to our layer 2 bias directly changes the output, right? So if our error is 5, right, if our prediction is 5 higher than our actual value, we could actually increase our bias by 5 and actually fix the error and have an error of 0. So the gradient on the bias is just the average of the output gradient. All right, so once we have our gradients, we can use gradient descent, which we learned in the last lesson, to update our layer 2 weights and biases. So let's first take a look at the original weights. So that's 0.5 and 0.2. Then we can set our learning rate, which is 1e negative 5. As you'll remember from the last lesson, you need a really small learning rate to avoid taking a step that's too big. Then we can update our L2 bias, which is just our L2b gradient times the learning rate. And we can update our L2 weights, which are just our L2 weights minus our L2 weight gradient times our learning rate. And when we're done, we can take a look at our layer 2 weights. Okay, I had a small typo there. I typed L2 instead of LR. So now we can see both of the updates. So we have our gradients are the same shape and size as our parameters. So these updates can work properly. Okay. All right. Now what we need to do is calculate our layer 1 gradients. So let's take a look at how the forward pass worked for layer 1. So we can see that our layer 1 outputs were scaled by our layer 2 weights to get the output of layer 2. So another way to think about this is multiple inputs were connected to multiple outputs through the weights, similarly to what we saw before, right? So I11 is connected through W1 to the first output. I12 is connected through W2 to the first output as well, right? Because this is I11 times W1 plus I12 times W2. So to find the gradient of the loss with respect to the output of layer 1, we have to scale the gradient by the layer 2 weights. So if we go all the way back up to this back propagation diagram, you can actually see that step here. So we go from our layer 2 output gradient to our layer 1 output gradient. And that's because our layer 1 output is multiplied by the weights to get the layer 2 output. So any change to our layer 1 output will be scaled by the weights, right? So if the weight value is 0.5 and we adjust I11 by 10, it'll be multiplied by W1 before it gets added to the output. All right. So this is how we can reverse our forward pass to actually ensure that we're correctly accounting for that scaling. So we take our output gradient and then we transpose our layer 2 weights and we multiply them out to get our layer 1 output gradient. And we can see how this preserves the correct connections from the forward pass. So we can see that the first output is connected through the first weight and the second weight to the first and second elements of the first row in layer 1. So this is the exact same thing from here, except now it's in reverse. And this will give us the correct gradient with respect to each of the parameters in the output of layer 1. So let's go ahead and calculate this. So we'll say with exp, the L1 activated gradient equals the output gradient times the L2 weights, but transposed. And this ensures that we multiply each row of the output by each column of the weights. Okay, so let's take a look at our L1 activated gradient. All right, so you can see we took a 5 by 1 matrix, the outputs, and we multiplied by a 1 by 2 matrix, the weights, and we ended up with a 5 by 2, which is the gradient with respect to the outputs of layer 1. All right, now what we want to do is calculate the gradients against the layer 1 weights and biases. But first, we have to pull the gradient across our ReLU nonlinearity. So we have to take a look at what the derivative of the ReLU function is. So to take a look, let's create a range of temperatures from -50 to 50. And let's go ahead and plot these out. We'll plot out our temperatures, and we'll use the ReLU function on the temperatures also. And remember, the ReLU function is just the max of 0 or the temps. So anything below 0 is set to 0. So we can see what the ReLU function does to these temperatures. Some of them are just set to 0. Some pass through the ReLU function and are preserved. All right, and in this particular case, the slope is 1, right? Because of how we arrange these temperatures. The arange function gives you temperatures with a gap of 1 between them, or gives you values with a gap of 1 between them. So the slope of the ReLU function is 1 or it is 0, which means the derivative is 0 or 1. So to show you what that looks like, let's first run an activation function over our temperatures. And then what we'll do is plot the derivative of the temperatures. So we'll take each temperature and subtract the previous temperature. And the NumPy roll function will just shift values in a range. So basically where -50 was, it'll put -49 and so on. So you can actually subtract the values from each other. So you can see the derivative of the ReLU function here. It's either 1 or 0. And at 0, it's actually undefined, but by convention, we set it to 0 at 0. So the derivative of the ReLU function is either 0 or 1 for our purposes. In reality, part of it is undefined. So what we can do is go ahead and multiply our layer 1 activated gradient by the derivative of the ReLU function, which we can use the Heaviside function to calculate. So the Heaviside function will return 1 when a value is over 0, and 0 when a value is below 0, and it'll return 0 at 0 because we passed in 0. So we can go ahead and take a look at our L1 output gradient. All right, so we can see what we did here. We took the L1 activated gradient and we multiplied each element by the output of Heaviside. And we used just a regular multiplication here, not a matrix multiplication, which means it multiplied each element by each other element. So it set one value to 0 because this was below 0 in the forward pass, which meant that it didn't contribute to the output gradient. Right? If a value was below 0 when it hit the ReLU in the forward pass, it was set to 0. And any value that is 0 doesn't contribute to our predictions in subsequent layers, right? Because if you multiply it by a weight, you still get 0. So this makes sure that anything that didn't contribute to the gradient in the forward pass is also properly reset in the backward pass and doesn't contribute to the parameter updates. Then we can calculate the layer 1 weight gradient, same way that we calculated the layer 2 weight gradient. We just take the input to layer 1, which is just the input, we transpose it, and we multiply it by the layer 1 output gradient. And then we do the same thing with the bias gradient that we did earlier. We take the layer 1 output gradient and we take the mean. And then we can go ahead and update our weights and biases. L1B gradient times the learning rate. So those are our updates. And we can take a look at our layer 1 weights and our layer 1 bias. Okay, so that's backpropagation. We just backpropagated through 2 layers and did gradient descent at each layer. It's important to note that I combined backpropagation and gradient descent, but this part, when we update the weights, is called gradient descent, and this part, where we calculate all the gradients, is called backpropagation. So here's the rough algorithm we followed when we ran the whole network. So we calculated the network forward pass and we got our output. We computed the gradients with respect to the output using MSE grad. And then we looped through each layer in the network. Here it wasn't a loop, but in our implementation, it will be a loop. And we computed the gradient across the nonlinearity. Then we computed the gradient with respect to the weights and biases. And then we computed the gradient with respect to the inputs to the layer. And then we were able to update the parameters using gradient descent. So in a lot of implementations of neural networks, you may be using an algorithm slightly different from gradient descent. The same principle of gradient descent applies, but there are some algorithms that modify how you do the updates slightly. So that's why it's important to understand that they're actually different. The other thing that's important to understand is our batch size. So the batch size is the number of training examples that you pass at once through your forward pass and your backward pass. So the larger your batch size, the more examples you're passing through at once. So in this example, our batch size was 5, right? We passed 5 rows of data in. Now, let me scroll all the way back up where we did that. Yeah, so we passed in 5 rows of data. These were our inputs. And that means that we had a batch size of 5. Now, the larger the batch size, usually the better a network performs, the faster it will run, just in terms of time it takes. But it can actually descend less effectively. So gradient descent can be less effective if your batch size is larger, because you don't get as many chances to update your parameters. So if you set your batch size too small, the network won't run effectively, like it won't run very fast, and the gradient updates can be too influenced by single training examples, and it can pull the gradient back and forth. But if your batch size is too large, your network can take a long time to actually descend because you're not giving it enough chances to update its parameters. So batch size is really important, and there's a little bit of an art to setting the right batch size, but we'll cover batch size in future lessons also. Okay, now we know how to put all of this together. We have done a forward and a backward pass, and we can actually code up our neural network at this point. So let's go ahead and load in our data. So we're going to use 3 predictors, Tmax, Tmin, and rain, and we're going to try to predict tomorrow's maximum temperature. We're going to use what's called a scaler to scale our data. So that's going to make our data have a mean of 0. So some data is below 0, some data is above 0. Just out of the box, all of our temperature values are above 0. They come from California, where it's usually pretty warm. So scaling our data helps us activate our ReLU function and train the data, train our algorithm and our network more effectively. And then we're going to split our data up into 3 sets: a training set, a validation set, and a test set. So the training set is for training our algorithm. The validation set is for tuning hyperparameters like batch size and learning rate as we're training the algorithm. And the test set is for doing the final evaluation. The reason why we split up the validation and test is you can actually tweak your hyperparameters to overfit to the validation set. So the test set gives you an unbiased way to estimate how good your algorithm is. So now we can actually go ahead and initialize our layers. So we're going to make it so our network can have as many layers as you want. So we're actually going to create a list called layers, and we're going to loop through the inputs to compute the weights and biases for each layer. So to the list of layers, we're going to append two NumPy arrays. We're going to append a weights array, and we're going to append a biases array. And the weights array, I'm going to scale so that all of the weights fall between negative 0.1 and positive 0.1. And this can make the network converge and descend a lot more effectively when the weights are properly scaled. So you can feel free to mess around with different types of weight scaling. And then the bias, we're just going to initialize to 1. And you'll notice that the shape of the weights is the number of columns in the previous layer by the number of columns in this layer. And the shape of the bias is 1 by the number of columns in this layer. And that's similar to what we did before, right? This is necessary to actually multiply the matrices properly. And then we'll return layers. And then we'll set up a layer config list, which will just configure how many layers we want. And the first layer will be the input layer. So we're telling the network, hey, we're going to input 3 features, Tmax, Tmin, and rain. Then the first hidden layer is going to calculate 10 features from those 3. The second hidden layer will calculate 10 more features. And the last layer will just output a single number, which is our prediction. So we can go ahead and initialize our layers and take a look at them. So these are our layers. Each layer is just a list, and the first element in each of those lists is the weights. The second element is the biases. All right, now we can write our forward pass. This is just going to be a loop. So we're going to take in our inputs. So these are the values that we're feeding into the network. And we're going to take in our parameters, so our weights and biases. We are going to store our hidden states. And these are just the inputs to each layer because we need these in the backward pass. If you'll remember, when we're calculating the gradient with respect to the weights, we need to take the input to the layer in the forward pass and multiply it by the gradient. So we're just saving that input in this hidden list. And then we'll say for I in range len layers. And what we're going to do at each layer is multiply our input, which is this variable batch, by our weights for the layer. And we're going to add in our bias. And then if we're not at the last layer, if we're not at the output layer, we're going to apply the ReLU function. Because we don't want to apply ReLU on our output layer. Okay. And then we'll go ahead and append the inputs to each layer, which is the same as the outputs of each layer, to our hiddens list. And we'll go ahead and return our outputs. So at the very end, batch will just be one value at each row. It'll be our prediction, and we'll return our hiddens. So that's our forward pass. Then we can pull down the loss functions. So after we do our forward pass, we'll want to actually calculate the loss with respect to our model output. So we'll go ahead and pull those 2 functions down. And then we need to write our backward function, which will take in our parameters the hiddens from the forward pass, our gradient, and our learning rate. And this time we're going to loop through our layers backwards. The backwards pass, right? So this will go through from the last layer to the first layer. And then we'll say if I does not equal len layers -1. So if we're not at the last layer, we'll actually undo the ReLU function. We're not applying the ReLU function at the last layer, but at all the other layers, we have a ReLU function to undo. All right, so that's just going to undo the ReLU function. So hidden will have one more element than our number of layers. So I plus 1 actually refers to the hidden for the current layer. It's the output of the current layer. Because you'll remember how we are appending to the hiddens list. So then we'll say our gradient with respect to our weights is just the transpose of the input to the layer times the gradient. And our bias gradient is just the mean of the gradient, x is 0. All right, and then we can go ahead and update our weights. So we'll just take the W gradient and multiply it by the learning rate. And we can do the same thing for our bias. So we'll take our B grad and multiply that by the learning rate. And then we need to pull the gradient across to the layer below. And to do that, we're just multiplying our gradient by the transpose of the weights. And then at the end, we can return our layers. All right. Now we need to put all these functions together by using a training loop. So a training loop will take our data and pass it into the forward and backward pass several times. And each time we take our whole data set and pass it in is called an epoch. So with gradient descent, you need to use several epochs to train the neural network to actually descend properly and get to good parameters that minimize error. So we'll start out with epoch set to 10, and we'll set our batch size to 8. And we'll go ahead and initialize our layers again. It's nice to initialize them in the same Jupyter cell that you actually write your training loop. So you reinitialize your weights every time. So we'll loop for however many times we have epochs. We'll define an epoch loss, which is just going to be the average loss across the whole epoch. And then we'll say for I in range 0, train x.shape 0. So this is the number of rows in our training data. And we will use batch size as our step. So we'll create an x batch, which is just our x parameters, sorry, our input predictors. So that is just going to be I, which is the current loop index to I plus batch size. So it'll be 8 examples at each step. And then we'll define our y batch, which will be similar. This is our target, what we're trying to predict. Then we can actually get our prediction and our hidden states by running the forward function and passing in our x batch of data and our parameters. Then we calculate loss with MSE grad, and we pass in our actual values and our predictions. And we can append this to epoch loss. We'll turn epoch loss into a number instead of a list. All right, so that's adding our epoch loss so we can keep track of how effectively our algorithm is learning. And then we'll go ahead and run our backward pass. We'll pass in our layers, our hidden states, our loss, and our learning rate. Okay, so that's a training loop. And we can go ahead and run this. And we won't see any output because I forgot to add the print. So at the end of each epoch, we're going to actually test our algorithm across our validation set. And we can just do that by running only the forward pass of our network. And we'll run it across the whole validation set at once. So our batch size will be the whole validation set. And what we can do is we can print some stats about our epoch. So we'll print out the epoch number. We'll print out the train mean squared error, which is just going to be the mean of our errors. So it'll be epoch loss divided by train x dot shape. We'll divide this by batch size. So that's the number of iterations our algorithm will make in each epoch. And then we'll print out our valid mean squared error, which is just going to be the mean of our MSE between the valid preds and valid y. All right, so now we can run it and it should print some things out if I close my parentheses. All right, train x.shape 0. So that's the number of rows in our training data. All right, so we can see our algorithm is running and we can see how the mean squared error changes over time on the train and validation sets. So you want to watch this carefully, especially on the validation set side. You can see that our validation mean squared error actually increases after 5 epochs. It starts increasing. And that's a pretty common thing to see because your neural network will start overfitting to the training set. So one of the things you want to do is monitor the performance at each epoch and stop the algorithm if the valid mean squared error is going up. And I'll talk more about that later on and how that works. But after we run this network, we can actually take a look at some of our parameters. So we can take a look at the parameters for our first layer, our weights and our bias. We can also measure our error across the test set. So we can say prediction. Actually, I don't need the hidden states here. So say forward test x layers. And then we can print out the mean squared error between test y and pred. In the mean squared error function, the order doesn't matter. In the mean squared error grad function, the order does matter. So you may have noticed I used a different order here and here. And we can get our mean squared error across the test set, which looks pretty good. Okay. We learned a lot in this lesson. And in particular, we learned a really complicated concept, backpropagation. So if you don't get backpropagation, I really urge you to implement this yourself and to really go through the diagrams and think about how the weights are connected. It really helps me to actually write this out on a whiteboard and think about how all of the weights and inputs are connected to the outputs. All right, I hope you'll join me for the next tutorial, which is going to be about using a neural network to do classification. All right, thanks.